I wanted to give you a general introduction, kind of get us on the same page to make sure we're all excited about JWST. I hope you already are, but in case you're not, I hope to change that in the next hour. As you might know, on Saturday passed exactly 3 years since we saw this picture, and it was amazing. For me, it was almost a life-altering experience when I saw that. It was pretty amazing. I was in Paris at the time with other observers, and we were, enjoying the beautiful new images from JWST. It was a great relief. It was years of effort to get this done. So it was amazing to see. And now we are 3 years later, and we've been overwhelmed by the amount of data, by the sheer amount of new research, new papers that are coming out of JWST. It's been very exciting. And in this talk, I would like to summarize that briefly, but also show you a bit of history, how it all came to be, actually. So that works. So this is not James Webb, this is Hubble, another major telescope from NASA and ESA, launched in the 1989, if I remember correctly. And it was a 2-meter UV visible light near-infrared telescope, but very limited to the near-infrared section. That's important distinction. But it already showed us beautiful revolutionary science, such as this Hubble Ultra Deep Field, which showed this beautiful amount of teeny tiny dots, all of single one of them being a galaxy, except this one. This one is a star, I believe. And it just showed, how vast is the space, how far we can reach. But it also made us realize quite quickly that there is a limit to how far we can reach with just Hubble, with just the optical and near-infrared light. We want to push further. And further, for astronomers, often means infrared, because as you might know, universe is constantly expanding. The specific rate of that, and is it going to accelerate forever? I think it's still an open question of some sorts. But in general, it's expanding, which means it's getting redder. And if you want to get to the infrared, we need to usually go to space indeed. It's becoming very challenging to observe in the infrared, especially in the far infrared, from the ground. So it was a natural choice that already, I think, even not short after or even during the Hubble preparation launch, there was already concept for a new, even better, even bigger observatory to do that. So Hubble, of course, was amazing. It delivered us so many amazing pictures. And I think it's kind of the service to him what I'm going to do today, because I'm going to show a lot of pictures from Hubble and how JWST is doing better. But this is by no means mean that this wasn't great, and it still is actually still operating after 30 years, which is remarkable and gives us some hope for how long James Webb is going to last, I hope. But we saw many amazing stuff, not only in terms of images, but also in terms of science. For me personally, the galactic science, when it comes to what we've been able to observe when it comes to the accreting stars, UV light, it's very important to observe accretion in the UV. This is the most direct tracer of how much mass is falling into the protostar. And so it's been very important for us also because we can do this on a periodic manner. We can come back to the sources every day basically and try to check how's the accretion variability changes. It was very important for us. I know for extragalactic science it's been transformational when it comes to measuring the Hubble constant into understanding, the expansion rate of the universe. Also in just, as I show you, the sheer amount of galaxies that there exists. So, but of course there's need for more, or need for better. And to that end, we needed to go also bigger. This is kind of obvious because we need more collecting power for sensitivity. We need also larger dishes for resolution. And that's especially important in infrared because, of course, with longer wavelengths, we lose our resolution. We need to compensate for that. So even though JWST is bigger than Hubble, 2 meters versus 6.5 meters, we achieve somewhat comparable resolution in the mid-infrared, just because the wavelength also increases. And it was clear that it cannot be done in one piece. And as you see, it's a famous now honeycomb structure of the dish. We needed to fold it to send it to space. So I hope to share some details of that. Just one more note, indeed, that Hubble covered from UV to tiny bit of near-infrared, but James Webb is really a powerhouse when it comes to studies of here. We benefited a lot from the Spitzer. This is one of a main legacy telescopes for us when it comes to understanding. And now in terms of comparisons, it's been great to see one-to-one what Spitzer and JWST can see both. And I think in one of the projects we actually have a very nice direct comparisons between Spitzer and MIRI. So that's going to be very exciting. Spitzer, to be fair, went a bit further in wavelengths. So in terms of kind of a backstory, how JWST came to be, and I think I have some details on that later, but in general, it's been a challenge to push it further. First of all, even the instrument that does from 5 to 28 microns was at some point a big question mark if it's going to happen. So there was a big push from community to make it happen. I'm very happy they did. But it doesn't go as far as Spitzer. So for example, there's a nice line of silicon at 34 microns that we don't cover. We don't cover the most basic, the lowest energy of H2 rotational transition. So there are some limitations, but this is going a bit into details. The point is, we have this very unique coverage. None other instrument can do what JWST can do at the moment, especially in the 5 to 28 microns. Up to 5, we reach that sometimes with VLT, with different instruments in Chile. But 5 to 28 is really unique for JWST. So indeed, I think one of the main drivers, at least the way I understand it, was to push further into the outer galaxy, into the outer space, basically going back all the way to the first stars, first galaxies, and trying to see the epoch of reionization. So many of those first going as far as we can in that sense. And that, of course, is realized by using infrared wavelengths because of the expansion of spacetime. So that in general means that within the infrared we see things much differently compared to visible light. For just an example here of a galaxy which shows mostly stars, scattered light from the dust. With infrared we peer right into the galaxy and see what is happening inside it. We see warm dust, we see protostars much closer to regions when they are forming, not just the surface of it. So it's incredibly important to be able to access the infrared wavelength range. So how did it came to be? First sketches on a napkin in the early 90s look like this. Sorry, 96. But indeed, some of the structures were already there. If you recall the official design of the JWST, so we already had the sun shield, which is needed. Of course, we are in the infrared. We need to be as cool as possible. And we also have already the foldable mirror. It was very clear from the very beginning we need to have a foldable mirror to be able to launch it to space. And science instruments were hidden behind the back, also well hidden from any kind of sunlight. In 1999, it was decided that the project is going to proceed. First named Next Generation Space Telescope, then renamed to James Webb Space Telescope. And this is the final design. As you can see, it looks fairly similar, probably a bit cooler because of the gold dish here, which is great for reflecting of the infrared lights actually. And those nice 5 layers of the shield that give you basically, if you use a sunscreen, it gives you a SPF of 1 million basically. So it's pretty good. And we have a foldable mirror, foldable secondary. It all opened up as we went to space. I think this is a launch video. Yeah, I think the sound is only on me, but you don't need the sound. I'm just gonna talk a bit. So on Christmas Day, on 2021, we were witnessing the launch of the James Webb Space Telescope. It was a very thrilling experience. As you can imagine, we started in the early 90s, before I was born, thinking about the space, this mission, and now it came to fruition, right? After many delays. On another personal note, when I started my PhD in 2016, I was planning to work on it by the end of my PhD. That obviously didn't happen. Made yet another postdoc, and then I came back to actually work on the data in Leiden, where I am now. So, all of this pressure, 30 years, hinging on this launching point, basically putting it on a rocket and sending it to space. Kind of frightening, but it worked out great, right? I mean, we saw the launch from the Kourou in the French Guiana, from the ESA rocket Ariane, and it delivered. It delivered so nicely that the initial expectation lifetime was 10 years. but because we used so little fuel on corrections for the orbit, we now are expecting 20, which in terms of science result is actually a dramatic increase in what we'll be able to do. So it's really remarkable that we've been able to do it. I'm gonna skip to the one more moment, which is very nice. Yeah, basically the moment where it separated from the rocket and went on its own alone journey. Well, it's not alone. There's plenty of space at L2, plenty of other missions like Gaia. So we had a nice company there. And now the crucial moment, if it didn't unfold, we won't have power. So that was also very scary, I must say. Well, I'm still tense, but I know it's gonna happen. Yeah, but that was the moment like my heart stopped for a moment. Yeah. And yeah, I think the launch went great. Everything went as expected, or as they say, nominal. So everything went up to the plan, and we will. Do we get it?
Yes, go web.
It's not unfolding. Okay. Okay, they actually fast forward. There we go. Okay. So we got our power. So that means that was the last sight of the JWST as we saw it. So then it started unfolding and calibrating in the process that lasted more or less 6 months of different processes involving actually aligning the mirror. So as it unfolds, it wasn't perfectly one shape of a mirror. You see those tiny cracks and wiggles. It all needed to adjust. It took a while. Yeah, we have a little simulation here, basically, you know, pointing at the nice point source, a star, trying to see how big of a improvement we get in terms of the sharpness of the image. It's of course crucial to get a sharp image. Hubble knows something about that. It kind of failed to do it the first time. It got a nice correction and it solved the problem. Again, no hard feelings. But this is how the process was realized. It was a very meticulous process of aligning, and thanks to that we have such sharp images until this day. So now we have a nice and sharp telescope focus. So first of all, the improvement, that was actually the first image. I told you that the image on the front of the Carina was the first image, but I think the first image we actually saw was already this, when they show basically the focus and calibration that we've been able to achieve. So basically the sharpness, but it already showed us so much, right, in terms of the improvement. So comparison here is comparison between different infrared missions. So we have WISE, and we have Spitzer, which I already mentioned, and we have JWST. So as you can see, we are progressively getting better and better when it comes to sensitivity and in terms of resolution as well. And so many tiny dots here that were basically invisible here are starting to make sense now, but also the structures that we now see, this is probably some sort of a nebula star-forming region, I don't know. And we see basically all the structures getting very sharp. So it was promising us a lot, and it delivered. So this is the overview of the field of view of the James Webb Space Telescope. So if you imagine JWST pointing at the sky, all it sees is this, and then of course we get a choice of which instruments we want to use. So I'm gonna have another lecture today, sorry for that, but there's gonna be another one on NIRSpec, on NIRCam, on all those instruments, basically going a bit more into technical detail of what they can do, what they can deliver. But basically you see that we have a NIRSpec, which is a powerhouse when it comes to spectroscopy. All those fields can be also used as a spectroscopy, which is amazing. We have NIRCam, which is basically delivering all those beautiful images. To be fair, most of the exciting first releases were coming from NIRCam, but also our humble MIRI, which does mid-infrared wavelengths from 5 onwards, and it's closest to my heart. We have NIRIS, which is a slits spectroscopy instrument, and we have a fine guide that shares on that, basically allows us to point the telescope where we want it to. So what were the actual scary moments, except like unfolding of the sun shield? That wasn't actually that scary. Scary thing was when the micrometeoroid hit us in the mirror, and we saw it. Of course, we don't have a camera pointing at the mirror, which would be cool. But what we have is the tracing of, indeed, as you saw, the alignment process. So we have a very precise information how the mirrors are aligning, and we could clearly see that something's off. So now we could definitely identify that it was probably to the micrometeoroid that hit it. I don't know the size of it, but it must be tiny. And basically, it left a permanent mark, so we can imagine a tiny speck on this mirror that's being left, and it's something to be corrected for, right? But as long as we know about it, it's fine. But it triggered a whole procedure now that whenever telescope is pointing somewhere, we need to consider whether it's pointing in the direction of light or against it, right? So basically, anytime JWST can, it points, basically it stands in the back and all the micrometeoroids that could fall on the direction of the flight are hitting the sun shield. So we try to avoid as much as possible this risk. But then from the probabilistic perspective, it was like 1 in a million event. So I don't think we are expecting anything that massive, but it's better to be safe than sorry. Another scary moment also for me was the MRS shutdown, which lasted about 3 months. So MRS is one of the modes of the MIRI instrument, the spectroscopic mode. I would say roughly in August, September 2022. So 2 months after started actual science observations, the MRS went into the safe mode. We didn't know what happened. We knew that nothing dramatic happened to the telescope. Everything was still working fine. But for safety reasons, the MRS stopped observing for like 3 months, which from long-term perspective makes a lot of sense. But for me, it meant that I'm not going to get my data very fast. And I needed to wait whole another year for the specific data on the specific part of the sky, which was a tiny bit annoying. But of course, now it's fixed. It's great. It was a little torque that was caused by the rotation of the grating wheel. So now the trick is that every time after a couple of rotations, just we do it in another direction. That was a simple solution to that. And it seems to be working fine ever since. Another thing with MIRI we realized was that, we realized that sensitivity is dropping rather quickly. So over the course of a year, we lost like 20-25% of sensitivity in channel 4. So as you can see, it doesn't really matter for channel 1. You don't know the channels yet. But basically at shorter wavelengths, it doesn't really matter. It starts to matter here. So we were a bit worried because it was like decreasing and decreasing, but it's stabilized. I don't know what else. I'm not sure we have a final answer on that, but maybe some of you know, I don't know. But basically it's probably related to some of the chemical reaction that occurs in the detector, perhaps some residue that causes it to slightly decay in a non-standard manner, because we do expect a decay of sensitivity in general. You know, electronics were out, but this was unexpected. But now it seems to stabilize. So whatever was happening, I think it stopped, which is great. We have some PSF anomalies, like for some reason you looked at your telescope and it was perfect, and then once your star image that we saw, these nice speckles, looks slightly weird. We have one or two of those events where suddenly something happened and we didn't realize only after the observation. But that's actually fairly easy to fix once you know when it happened and what was the actual shape of the mirror at the time. So nothing too dramatic. So I think that was the context, the history of how we arrived at doing science. And as I said on Saturday, 3 years ago, on Saturday we celebrated 3 years ever since we saw the first images, and they were pretty amazing. And the types of science we can do with JWST was, and the way it was envisioned to do, was to do first light and then reionization, basically 4 different blocks: galaxy assembly, and in general galaxy formation and evolution, formation of stars and planetary systems, and studies of exoplanets and origins of life. Well, that's not exactly true, because when JWST was first designed, we didn't know any exoplanets except the one that Wolfgang discovered, which I told you about this morning. And quickly, you know, it became a big field, right, over the scope of last 30 years. So now it's, of course, one of the crucial science themes, but definitely it wasn't when the JWST was first thought of. So we're gonna start theme by theme, going through some of the most spectacular results which JWST delivered over the course of its work. So we start with the early universe. Basically, JWST went and did what took Hubble more than 2 weeks to do in a couple of hours, which is frankly amazing. And that was the first image. Actually, Joe Biden scooped us on release of the image because it showed us a day earlier than the rest of the images, but fine. And then we saw a lot of those tiny little galaxies And then, of course, as we started digging through those images, that was just the first light, right? But as soon as we started looking into the images, so many exciting signs. But you can also see beautiful lensing and structures because this is a massive cluster in the center. And also the first program started delivering. So JWST had something called Early Release Science. So that was a program specifically designed not only as a research project. Of course, they have a lot of exciting science, but they were meant to become public immediately and to be taken very early. And the goal was that we basically can experience what kind of capabilities JWST has. So the programs needed to be brought, needed to apply different science techniques and different instruments, basically. And the goal was to make us, play around a bit with the telescope. And the data was about to go public immediately so that everybody can achieve this. So one of these was SEARS. That's a program basically doing imaging of galaxies. A lot of those taken beautiful data. So that, again, also became immediately public. People started looking into it. I think it really helped accelerate in the process of doing science that we had access to some of those early data. So that was a very nice practice. So this is another example. I'm going to do a lot of those comparisons, but this is just kind of amazing, the improvement we've been able to do. If you look at the shorter wavelengths of infrared with Spitzer, we already see that, those blobs becomes very visible. But as I said in the beginning, the real improvement, the key improvement, is also happening in the longer wavelengths. So if we look at the 24 microns, we are really struggling with Spitzer to see anything at the order of a couple of arc seconds. And now we can really resolve those things. Those things are all taking shape, and we can start looking back into the universe. So some highlights again from SEARS. This is, I think, again, more of a 3D visualization. I think it's pretty cool, which kind of allows us to look into the vastness of the galaxies that we've been able to observe with JWST. I think most of them have some sort of redshift emission, or maybe it's just a guess, I'm not sure. But basically it allows you to kind of imagine that we are moving through the vastness of space, looking at galaxies at various redshifts, right? Basically the redder they are, the further away we look. And mysterious red dots, we started seeing them quite early. Basically tiny red spots. Anna will give an entire lecture on this, so I'm not going to go into detail of that, but they were one of the most puzzling things that we saw in the early data. Basically, they seem to be extremely young, but already with sorts of evolution already ongoing. So can universe really, develop so fast that we can see them so early? So some another more beautiful examples of what we can do when it comes to studying the galaxies. We can see a lot of structures in those fields. I know now we see a Vera Rubin pictures. It might also take a bit of a different perspective, because to take those images takes definitely longer than taking the images with Vera Rubin. But then again, the JWST is the unique instrument to look in the infrared space. So this is the advantage that it has over any other telescope. And we can already see a lot of different structures within the galaxies. And of course, one of the first highlights when we started seeing those galaxies was people started, a little fight, a little run, who's gonna get the furthest galaxy ever. And we started hearing numbers like Z70, Z20, right? And it's all kind of nice, but we don't know until we do a spectroscopy, right? I mean, to some extent you can do this with photometry, but it still remains kind of in a vague space of perhaps it could be something else. Unless you do a spectroscopy, you identify the lines, you measure the redshift. So all those Z17, 20 have been not confirmed so far, but I wanted to highlight that one of the greatest things about JWST is spectroscopic capabilities. And in this case, with the new spec microshutter array, which I'm going to talk about a bit later, we can actually see spectroscopy of many sources at the same time. And I'm going to tell you later how. But basically, we can point at different galaxies, we can open our microshutters, and we can take the spectra. And as you can see, the same lines of hydrogen and oxygen are moving to higher and higher redshift for different objects. And you can see the structure even changes, right? So you can start studying those different galaxies as they evolve with time. So that's the big power of JWST. Record holder, I mean, we like records in the end. So the record holder now is at Z14.44. I think in May 2025 was the new paper, 200 million years after the Big Bang. It's pretty amazing how far we can look, although it looks just a few pixels, but still pretty spectacular how far we can look with JWST. And this is all again because we can reach the infrared wavelengths with that sensitivity. So as I said in the beginning, one of the key goals is also study the epoch of reionization. And I think in this paper we saw nicely that it might be possible to actually study that, because we saw these very high redshift galaxy at Z13, so not that far off from the furthest that we know so far, already showing hits on Lyman alpha emission. So basically it means that Lyman alpha could already, the hydrogen emission line, could already penetrate through and get to us, which means it wasn't captured. So you know, maybe the universe already started reionizing and let photons run free, which is also a pretty nice hint of what can we study in the early universe. Maybe we indeed are able to trace the epoch of reionization. And another key aspect, galaxy assembly, how we can study the galaxy as they evolving, merge, and form stars. First of all, an example also from this year. So beautiful example of low and a bit higher redshift galaxies and their structures, right? So this is, one thing is to detect a galaxy, which Hubble was also able to do to the redshift up to 7. But the another thing is to actually resolve them and start studying them. So what JWST can do is up to those higher redshift also study the structure. So those authors basically see for the first time stellar disks at such high redshift, basically understanding how the thin and thick structure of the disk can develop in the very early times, right? So basically we're looking at 8 billion years ago here. So it's a very crucial time. It's also important for studying the peak of the star formation, because as you might know, something called cosmic noon around redshift 2 and 3, that was the peak of the star formation in the universe, right? So, and we still have limited means of actually studying that process, and this might be the way to do it, to actually see how that structure developed, how those stars could actually form at such high efficiency in that times. So some cool comparisons, basically showing what we've been able to do at JWST. That was also one of the first images of this nice galaxy cluster, Stephan's quintet. You can see not only the galaxies, and this is the NIRCam light, so basically a bit shorter wavelengths imaging up to 5 microns, but we have also MIRI, which shows that imaging at longer wavelengths up to 20 microns basically, which shows us very different structure, right? And we can really, using the mid-infrared wavelengths, peer inside those galaxies, which is pretty exciting. We also can nicely see that those galaxies actually, you know, there's a lot of structure between them, and if you go into mid-infrared, you can see that inside those there are already star-forming regions. So even in this chaotic process of galaxy mergers, we have star-forming regions somewhere between them. Another powerful tool with the JWST Space Telescope is the IFU, which we call integral field unit or integral field spectroscopy, which basically means that we not only get an image, for each image, in each pixel of the image, we get spectra, which means we can start studying how those molecules and atoms and ions are localized in such galaxies. That's a major technique used with JWST. And basically, on an example here in Stephan's quintet, we pointed the JWST pointed MIRI MRS, so this is the IFU available for the mid-infrared range, and it's been able to see that in the center we have nice spectra with silicate absorption, so basically a lot of dust capturing the light in mid-infrared. And as we move outside, we also get a peek into the jet, into the outflow of the from this galaxy, basically showing species like iron, argon, and neon involved with very high energies, with shocks, and with energetic radiation. So doing that kind of maps where we can actually look at spectra at different wavelengths is a very key technique to JWST. So on the topic of galaxies, again, Hubble did a great job in looking at how it looks kind of on the surface level, but with JWST we really can peer inside and see how it looks inside the warm dust, kind of closer to the middle of the galaxy, where most of the star formation actually happens. And something that was pretty cool early on was the phantom void that they detected. It's huge space, probably caused by some sort of feedback of supernovae that, and actually if you start counting those, there are thousands of those smaller structures, which are all probably caused by various events of supernovae that were exploding and clearing out the space around them. So that's a very powerful tool. As you can see, like, you kind of expect them here if you look at the dust structure, which is in scatter light, but you cannot really say a lot about it without going into the mid-infrared. So the true power actually comes from combining the two. So kudos to Hubble as well for that. And we have a nice comparison of what Hubble and what JWST can see again. As you can see, fairly empty structure here appears quite bright in the mid-infrared range with JWST, basically showing us what is happening inside those galaxies, which is beyond the visual wavelength range. Another comparison of two galaxies, that's a fairly recent picture, I think from a couple of weeks ago, basically showing us, again, kind of a bone structure of those galaxies, right, as we peer in with JWST. And this is, again, a combined image, which is the one that provides a complete overview. And here you can see clear evidence of what I've been talking before. So you have those blue spots here. Those are all young stars forming and basically irradiating and clearing out the space around them. That's why those spots are not as red, because there's just less dust and less gas around them. They cleared out the space around them. So this is a very cool for studying the star formation on a galactic scale. And this is a beautiful gallery of the FANGS team has provided, which studied many, many galaxies. FANGS project already actually started from the ALMA observations, but then basically they went on and collected all the data on the other telescopes, including VLT-MUSE, and now also JWST. And it really shows the power of the imaging techniques we have now with JWST in order to understand the star formation in the local galaxy, in the nearby universe. So coming to my favorite topic, star and planet formation. And by the way, the galactic topics will be covered in more detail on Thursday and a bit tomorrow by Darko as well. So stay tuned for that. I don't want to say too much about that because I'm going to start making mistakes because I don't know that much about it. I know a bit more about star and planet formation, but there will also be a dedicated lecture to that. So for now, just a brief glimpse of what we learned with JWST about that. So as we already looked at the Carina image, this is again the powerful transition we get from Hubble to JWST, started looking closer and closer to the surface and even deeper into the region. And also with MIRI, we can see even deeper in. Basically, you can see all those stars kind of emerging from behind it, right? So with the mid-infrared wavelengths, we're really able to scan this entire cloud and realize what happens, how the stars are forming there. Another example is this cluster, basically, that's a tarantula, if I remember correctly. And basically with NIRCam, we already start seeing the beautiful shape, but with MIRI, we also are sensitive to very different wavelength range. We start seeing also the pHs. Those are the polycyclic aromatic hydrocarbons, which are basically tiny carbon dust, right? They're mostly HNC, hydrocarbons. And we can see different colors basically showing where are they peaking. So this is also very useful for chemistry. And there's a dedicated program that studies pHs, or in general those regions of high radiation, because as you can see, the star in the center, it's probably causing a lot of this, and also those stars behind it, they all irradiate, causing this structure to first of all empty, but then also to excite the gas around it. My absolute favorite, prostar outflows. So the fireworks that kind of celebrate, they announce the birth of a star. Star is forming somewhere here. We don't see it actually even with JWST, so that also nicely shows with JWST limitation. We are in the near infrared range, and we cannot see what's happening inside. It's just too much dust on the way. And you can see this beautiful outflow structure. What we think is happening is that this bow shock here, we call it because it looks like a bow and it's shocking. And this bow shock here is basically the first time the jet emerge and hit the cloud. So we think, if we know the velocity, and we do know because we have 20 years of observations with VLT before that, so we know how fast it's moving, we can trace it back And it seems it all started more or less 10,000 years ago. So it's an extremely young protostar, at least on the cosmic scales. But there's another cool telescope that I'm not going to talk about today too much, but just to highlight that there are instruments which allow us to actually see inside. And inside this beautiful jet, there's a disk that powers this jet. So we can see that this is basically a millimeter dust surrounding the star. We actually don't see a star at all, also in the sub-millimeter wavelength. But the jet is actually a kind of a useful tool to study how these stars are forming, because if you see those tiny little shocks here, we think each of these is associated with separate accretion events. So the material was falling onto the star, and some of material is being released. And the more material is being accreted, is falling onto the star, the more is being released, simply speaking. So we think those are related. So we can maybe trace back the accretion history of the system on a couple of 100,000 years timescales, which is pretty cool. Another beautiful example, F1527. This is a bit more evolved protostar than this one. As you can see, we don't clearly see the jet in the center, which is kind of a surprise, I think. I think we kind of hope to still see some kind of jet in the center that powers this whole thing, but there's almost nothing. We have a paper now in prep, I think submitted, that's actually sees the jet that is super tiny, very close to the protostar in the far infrared wavelengths. So there is something powering this, but in general, it seems like most of this is actually just the bulk of the outflow, probably launched by some sort of a wind, which is much lower velocity than the jet, and basically a lot of irradiation from the star itself. You can see a tiny dust lane here. So the disk is almost straight edge on. So we see both light basically escaping only through the layers of the disk on this side, but there's almost nothing we can see in the center. And so you can also see various structures that happen, basically shaping the system. You can also see what happened here. You see stars and they start to disappear, also galaxies, a bit annoying. But you can start see them disappearing. And what happened there is that there's more and more dust in those envelopes, right? And you start cover your stars. So it's a very nice example of how dense those clouds can be. Another beautiful region, this is Ophiuchus. We see a lot of beautiful structure here. First of all, this kind of veil-like stuff. All of this irradiated by those two stars, or maybe those three. It's kind of cool that, you know, one star can do such a beautiful spectacle on the sky. But also the beautiful thing, you can see a dust lane here. This is actually the disk that we don't quite see yet, but I can show you a zoom in later, that basically there is shadow that is being casted by the star and as it being obstructed by the disk. And we have those tiny bow shocks here. This is another jet of a star that I don't think we see. Maybe a tiny bit here, but it's hidden inside, and we see kind of the effects of the outflow here. And again, we see a beautiful structure that goes all the way here. And yeah, again, if we zoom in, play around with the contrast, we actually can see that there is a disk. And there is another one that is being causing this dust lane here and the shadow, but we can also see a similar disk to the one on the previous picture. And again, we can do a nice comparison with ALMA, something I really like doing, to just compare how those structures look in different wavelengths. And you can see that the alignment of this disk is perfectly makes sense compared with the jet that it launches, because you can see a tiny, tiny jet being launched from here. Another nice example is how we can actually study those is that when you think about those outflows and shocks, most of the gas that we see is actually H2, so molecular hydrogen. And molecular hydrogen is perfectly symmetric, right? So it doesn't really emit infrared, it doesn't have a permanent dipole moment. So it usually emits at a bit higher energy. So you need quite high temperatures to excite it, which means infrared is actually the best way to do it. And so some of this you can see already here in the blue. This is Hubble, which probably traces some of the visible transitions of H2 or maybe even H1. But we need we need infrared wavelengths to actually see it. And this is what we see once we move to JWST and NIRCam, right? This is beautiful structure of H2 gas being ejected from the system. And the protostar is forming somewhere here. You can see also this characteristic specs of the point spread function of the JWST telescope. So One of the another ERS programs, so those early release science programs that I told you about, was dedicated to ices. So basically, while the gas we observe as emission lines, the ice is absorbing the light. And it's absorbing a lot in the infrared wavelengths. That's why JWST is also great to study that. And how we can actually, well, we know basically that there's a lot of ice in those clouds that are forming stars. But unless we have a star that's kind of behind it, like this one or this one, we can start having a nice source, kind of a flashlight, right, that peers through and allows us to detect what we are seeing with this in this cloud, what kind of composition of those ices have. So there's a lot of absorption. Each of those, throws you see in the data is a different ice species, or in this case water, but you also see a lot of complex organic molecules. I have a better spectrum in a second. Yeah. So for example here, first of all, you see this broad range. This is all absorbed. Normally you would see something along this shape that would be the spectral energy distribution of a protostar if it wouldn't be extincted by the dust that's on the way. So you can see that this is all silicates that absorbing most of the broad things, but also this broad thing is just water ice that's absorbing light in the mid-infrared range. But things start getting interesting if you are able to resolve this. And that also means resolving spectrally. So this is the key. JWST might not be the massive spectroscopic tool in terms of resolution, right? We achieve resolution of R roughly 3000, which in velocity translates to roughly 100 kilometers per second, maybe a bit better. But in terms of ices, it's a dramatic improvement what we had with Spitzer, which had a resolution of between 100 and 1000, or 300, not even 1000, I think. So it's really a dramatic improvement in that sense. And you can see now that only with resolution, if you are able to spectrally resolve those absorption features, you can start distinguish different species. So we are in a very exciting regime here where we see formaldehyde, we see methanol, we see ethanol, we see HCOH, I forgot the name, kwas mrówkowy in Polish, and we see CH4, NH3, so ammonia, and so we have a lot of those species, CO2 ice as well, a lot of those different ice species that we think, so that's the key part about ices, we think most of the complex organic chemistry that is then inherited into planets is formed in the ice stage. So basically ices are a very nice place for molecules to meet, right? So they meet mostly hydrogen, for example. You start with water, you have a lot of water ice, you have a lot of carbon monoxide ice, CO ice, that is in the near spec range that you don't see here. And you start meeting the molecules and they grow larger and larger. And it's very exciting to trace that process with JWST. So this is a very exciting paper from IRAS-2A. This is a protostar in Perseus molecular cloud, roughly 1000 light years away. And what you see here is a very prominent emission of ethanol. So the press release for that was called Cheers, because it's the alcohol we drink. So, but also methane, also very interesting, the formic acid, oh, that's the name. So formic acid that we see quite prominently here, a lot of those different species that, then chemists can take to the lab and see, okay, so what for molecules, what more complex stuff they can form, what are the basic ingredients for life that we can start building here. It's a very spectacular that we can see this with that resolution, and detailed ice modeling can reveal which species are tracing which specific peaks. But the important part is you need a laboratory data. So this is where interaction between the lab and observation is crucial, because you actually need laboratory data to understand what kind of different mixtures of ices you can have. On topic of planet formation, this is the actual beautiful disk resolved with ALMA, where you can see actual planet with a tiny disk surrounding it, we think. So there's a dusty structure around the planet. You actually don't see a planet, we see a dust that surrounds it, which is probably still accreting. But what was cool in this regard with JWST, that when we looked inside this, we see a water here. So it means that there's a water in the inner regions of the planet forming disk, where planets are actively forming right now, which is very cool because it helps us understand how we can actually deliver water, for example, to planets, right? We have a lot of ideas about how water was delivered on Earth, and this is one of the key pieces to this puzzle. Maybe I'll skip that, sorry. Dying star, this was particularly beautiful one. You can see the star that's more of a AGN star that's already shedding a lot of dust, and because of its rotation, or maybe it's a binary, I don't remember. But basically it is rotating and shedding all of those dust structures around it, which is pretty cool. We have some dying stars also after they explode a supernova, beautiful improvement from compared with NIRCam and NIRI, different layers. Again, we can see a beautiful structure that's becoming clearer, and with NIRI. We see another transition, there's a Crab Nebula, so beautiful supernova remnant. With NIRCam, beautiful high detail structure here. Another cool thing about JWST is able to follow up on stuff that's happening on the sky as we speak. So basically time-sensitive observations. So for example, that's a nice example where there was a kilonova that exploded, and JWST was able to follow up very quickly observations. Basically, where kilonova is a merger of neutron stars. And basically it showed us a beautiful tellurium, which means it's being produced. So we theorized for long that the mergers of neutron stars can produce some of the heaviest elements. Actually, evidence for that was given before JWST when we saw a gravitational event and were able to follow it up with VLT observations. But this is another cool example what kind of chemistry we can probe. Not only the stellar chemistry, interstellar chemistry where we form planets and stars, but also the chemistry of the universe in general, how we form the most massive atoms. Field of exoplanets is also booming. We're gonna get 2 nice lectures from that from Elizabeth. So, but I cannot not talk about it because it's super cool. CO2, carbon dioxide, already in the first release. We have this beautiful detection in the gas giant, beautiful water feature here. But it's already a nice, worth explaining here. The white dots are the actual data and blue is the model. So here, I think everybody believes what they see, but we're gonna get in the example where it becomes a bit more complicated. So, but you can definitely, they try to fit the model to this, right? And basically this is what they get. It's pretty clear it's water. Here, in this case, also very clear detection of sulfur dioxide. This was particularly cool because chemical model showed that sulfur dioxide needs to be formed actively, right? So it's not a residue after the formation. It needs to be actively produced by the UV light from the star. So we see active effects of photochemistry onto the atmosphere of an exoplanet, which is very exciting. A nice imaging of exoplanet. We basically using the coronagraphy method, using NIRCam and NIRI, basically occulting, covering the star, which is here. We can recover the signal of a planet, which is very prominent here. And that's again why it's useful doing it in mid-infrared. As you can imagine, typical star is usually very bright in the visible range. As we go to infrared, the star light decreases, but the planet light, because it's hot around 1000 K, increases in the infrared. So we can nicely increase the contrast by moving to different wavelengths. And this is what we also see here, how clearly it is seen in the 15 micron filter. A nice bonus, eye candy solar system, but there's also a lot of exciting science going on around it. Like for example, this beautiful Jupiter with some auroras in the north and south. Beautiful family picture of Jupiter and its nearby moons. And also the tiny ring, which is also very cool. And beautiful image of Neptune and its moon Triton, which is also very bright. And a couple of rings around it as well, and other moons. This is a beautiful example of another kind of a spot chance that JWST jumped on. I don't know if you remember the mission that, and now name escapes my mind, but basically it hit the asteroid, right, to change the course of its orbit. Sorry? DART, thank you. And it changed the orbit, and we expected a lot of dust to be released. And indeed, this is what happened. Webb was able to follow it up pretty quickly, showing this warm dust released from this asteroid as it was hit by human-made object. nice emission spectra from the comet. So another aspect of the solar system that we can study in detail is that we can look at the comets and their emission lines. So you can see, for example, water and carbon dioxide. And you can see already a comparison of two different comets. And you can see that carbon dioxide in this one is basically not present, where we see a bright carbon dioxide emission here. In the last 5 minutes, I think a couple of open questions I want to address, or maybe let's say controversies that are involving around research, because it's a very dynamic field. We have papers coming out every day, and sometimes some things slip through and they kind of get to the mass attention, and then there are some open questions like what we actually see here. One thing are jumbles, so Jupiter mass binary objects, beautiful, exciting results, which hinted kind of that the more you go into the brown, so usually you have something called the binary distribution function, where the more massive the stars are, the more likely they are to form binaries. And this steeply decreases. So basically, the less massive the star is, the less chance of having a binary. And then what they saw in this paper, or they suggested to see in this paper, is that when you go to the brown dwarf regime, suddenly you start seeing more and more of those binary systems. And that was a bit of a puzzle. Dozens of papers started coming out, like modeling, how do we actually make this happen? But all of this was based on the photometry. And as I said, spectroscopy is the key here to actually understand what's going on, because when we follow this up, or actually when Luhmann et al. Followed this up with the photometry, with spectroscopy, they actually don't see that those spectra are matching the brown dwarf spectra. So it's not quite likely that those are actually the brown dwarf systems. More likely that there is a coincidence of an object that's behind the cloud that's kind of affecting the emission. Basically, we are looking not at the source that's a brown dwarf in the cloud, in the Orion cloud, which we looked at, but we're looking at the source behind this cloud and kind of looks like a binary. So it's probably still an open question to some extent. Both authors seem to be very opinionated, but I think we don't see a good evidence for the jumbles, for the new category of exoplanets that was heralded also in the press releases in the media. So kind of a cautionary note on that. And another elephant in the room, of course, do we see life on exoplanets? So do we see a water world with hints of life? So that was the paper from from Madhu that in 2023 showed a hint of DMS, dimethyl sulfide, on an exoplanet. But then again, let's look closely. This is the data, the white points, and the blue spectra is the exoplanet retrieval from the atmosphere. So you can see that there's a lot of going on here in the model that you don't necessarily see in the data. You see a broad trend, right? And you can try to fit that the best you can. So actually, then when this press release was launched in 2023, they didn't even say it's a clarified detection. It was below 3 sigma. But they say there's a potential. When something happens, you want to be the first to claim it, right? So that makes sense. And they were quite careful about it. Of course, media does their own thing. But, everybody was quite excited about this, started following this up and started asking questions. And then came up another paper from the same group showing detection also in the mirror range. Hints of detection in the model in the mirror range, and also the MDS in the same data. But then again, we see points are the data and the error bars are here. And this is the well-refined model. So this was apparently above 3 sigma, but then some questions starts arising. So to what extent we can actually trust those fittings, right? Maybe for a non-expert, it's very not clear what's actually going on here. And then there was an interesting paper for Oliver Shorter et al., which kind of suggested that it might not be a water world. After all, it might be as well a lava world. At least it's both consistent with the data. And the whole DMS, or dimethyl sulfide, was made so exciting because DMS on Earth is produced only by plankton in the oceans. So imagining this water world surrounded by, where plankton is flying and producing this DMS was pretty exciting. But now, if this is a lava world, I think this is also inconclusive which kind of structure there is. We need to remember one thing about exoplanets, that this is not like we make an image. This is actually Mustafar from Star Wars. This is not a real image of exoplanet. So we don't actually see that, right? We see a spectrum, which looks like, a couple of points, and you try to fit the best model to it. From model, you get to the atmosphere, and from the atmosphere, we try to understand what could be the structure of the planet. But then also after the second paper, especially when the discussion came about the dimethyl sulfide in detections, paper started reanalyzing the data. And some of the fits that were done in other works, such as this one in Schmidt et al. 2025, found no key evidence for the detection of the dimethyl sulfide here. And also another paper by Taylor et al. Found that the data is as well fitted by a straight line as with the model. So I think the result is still inconclusive. I think, you know, this is the kind of the moment where at one side you really want to be the first one to bring out the big news. At the other hand, you have to be very careful. In the end, I think it's good the discussion is happening, but the way it's phrased as a detection sometimes might be a bit overstated. That's just my personal opinion.
I could maybe add, if you allow
Of course.
second. So they also organize also like the one-on-one discussion against these two guys, right? So it's nice way to get show to public how the communication can actually work without boosting big egos in such a big potential big discoveries. Yeah. But during that discussion also the both authors said that even if fits is composite, they will not know actually is it physically exploratory, because as far as I understood, those features were not uniquely assigned to.
Yeah. So it's more likely DMS than any other species in the model, right? But with a different setup of a model, you might as well reach a different conclusion. So it's not like, you know, it's not like a detection in the spectroscopy that typically you have a noise, you have a bright line. It's more of a fitting the model, right? And how much the model represents the spectra. But I think just this paper already says, like, you know, if you can fit a straight line with a similar kind of probability, then maybe it remains questionable. But yeah, I think the discussion should happen, and if anything, it triggers more observations. So another kind of puzzle, kind of I don't know, maybe a mild disappointment that, you know, TRAPPIST system was a spectacular one. We discovered 7 planets around very tiny star, many of them, I think 4, maybe 5, in habitable zone. So that was very exciting, and of course we pointed TRAPPIST telescope, JWST telescope to TRAPPIST system, and the first results that are coming out regarding those 2 planets seems to be showing that they are very dry. So there's no hints of atmosphere, which, you know, is kind of not unexpected given that, you know, they're here. But for example, we have a Venus in similar kind of regime, right, which has, of course, a lot of atmosphere. And it seems that, you know, the question starts to arise, what if all those planets are basically dry? So maybe all the hopes about the habitable zone are kind of, you know, too much for this tiny system, which maybe didn't host enough water to actually trigger any kind of biological processes. Because that's another important result that I kind of skipped before, that we see that formation of disks, of young disks, looks very different, or at least their composition is very different depending on the mass of the central star. So it seems that those low mass systems, and there's a lot of active research on the formation of those very low mass systems, is that they seem to be having different composition of their disks. So definitely there seems to be something going on here. But I think in general it's good to remember that JWST wasn't specifically built for studies like that. We have ELT for that coming up, or the Habitable World Observatory hopefully coming up, that will be able to do that, specifically that. JWST is really great tool, I think mostly for gas giants. This is really amazing for doing the transmission and emission spectroscopy there. But here we're really pushing the limits. Are we living inside the black hole? Probably not. Okay, that was another result that kind of came out. I just want to leave it out there. They saw a rotation, preferential rotation in the direction of galaxies, so it triggered some discussion, you know. If this is rotating, maybe we'll live in a black hole because black holes are also rotating. I mean, it's kind of elaborate, but yeah, it was fun to see that kind of discussion going on. So yeah, seems that JWST will be around for another 20 years. Thanks Isa and Ariane for a great launch. So seems we have a lot going on. So will we witness another truly Copernican-style revolution with JWST? I don't know, discovery of life, you know, solving the Hubble tension, all those sorts of stuff that could help us, you know, push the next frontier. I think it remains an open question, but I think it's a very exciting telescope. I hope I convinced you of that within this hour. And yes, let's get excited for doing some JWST analysis data. Thank you.